another one of these geothermal plates that you have is you have
some kind of
intrusive Okay. Another one you're going to have is when you have magmatism near the surface. Probably for a Lula, it's going to be a little bit deeper, just based off what some of the literature says. But again, nobody's ever really collected any kind of seismic data from these locations, so we don't quite know what it's going to look like. This is the kind of situation you have mainly for most of the world's like global when you have these this cooling granitic pluton with the sediment layer above it. And this is where you have like the geysers. California produces most of their energy from this kind of geothermal system, and also in Ladera in Spain, they have a gigawatt that they're getting out from geothermal. And then you have these extensional type of geothermals as well. You have conduction dominated systems. So we put together this slide to show what our actual plan was for getting started with this Alula project in Saudi Arabia. So the first thing we have been doing is doing a pretty extensive literature search, trying to understand better what the resource is going to be done. A little bit of mapping and geophysical surveying we're going to be doing in connection with our collaborators at Enviro and Geothermetics. And then this whole project is looking like it's going to start later this quarter, if not early this quarter. So we have a couple of internal things that we need to do. We want to hire a reservoir modeler, somebody who has a lot of experience working on these geothermal sites, and a couple of drilling engineers to actually start getting these initial geothermal gradients done, so we can really understand what the reservoir is going to look like a little bit more. And these slides just talk about in a little bit more detail some of the data that we're going to be collecting and going to analyze here over the next few years, as we start to understand a little bit more about this location. Mainly focused on a lot of like MT to be able to understand the depth of any potential water tables that's going to be on this side. And we're going to do a lot of slim hole drilling and things like that to get geothermal gradient maps and understand better what the lithology is like. And that's what is going to talk about a little bit more in this slide. And that's pretty much where we are right now. We're pretty interested to get the project started and getting some data collected, and then maybe in the future we can talk about do it alongside this research group and better characterize these resources, and down the line what we're going to want to do is couple the stimulation job, if it is EGS system, with the core electric fracturing technology that we've been developing. And I think that's the last slide that we put together here. Yeah. So anybody have any questions or things you want to discuss now?
We're on YouTube, so Mary Beth can probably see us and hear us now and chat with us.
I have a question, Paris.
Oh, is she hey.
Paris, I wanted to ask, as you acquire these different kinds of data, what's your plan to integrate them? So there are different measurements and different physical quantities, and all in the same region, I guess, but sort of not exactly collated. So there's a whole sort of, and then they'll be from different times. So how are you going to integrate them? And also, do you have an idea for the uncertainty quantification? to include when you do that? I know it's a big question, but I think it's a good discussion to start.
Yeah, and I think I do want to say again, like I'm obviously focused on the fractional technology development, and Mary Beth and Amar are the ones who lead this geothermal development. So, once you can get on, better talk about like what the actual plan is for developing these fields. But at a very high level, what we've done is we put together that consortium of different kind of partners between our company, Geothermex, and NREL. And then we're going to be using a lot of the local data that we have on these sites, mainly topography data, and integrating that with the data that we're collecting right now to better understand what the geothermal gradient is going to be in these locations, and if there's any kind of fluid source underground that we can use. So Mary Beth says she can see us on YouTube. Does that mean, how does she communicate with us from here? Laurent?
So she can type in the YouTube chat.
She can type in the YouTube chat.
That's all I could do. Yeah.
Okay, I guess that's fine.
Should we be following the
So I have a
YouTube
question.
chat?
There's a delay, Doug, so you can go there if you want, but it's.
How do we find that?
Oh, if you go up on, there's a little button that says live on top of your Zoom. I think if you click view stream on custom live streaming service, it should take you to the YouTube page. And then once you get to my YouTube page, you click on live, and then you'll get the stream there.
Yeah, I have a quick question. Why couldn't we just use like a different Zoom link for the meeting instead of this one?
So this meeting is being restricted to MIT people, and I added an exception yesterday. It promised me that it had sent Mary Beth an email, and apparently she didn't get it. And Mary Beth says hi on YouTube.
Oh,
so and once the meeting
Okay.
started, I could no longer edit its setting or have the exception resent. So I didn't want to kick everybody out. So that's my plan B.
Okay. Okay. Mary Beth, while we're chatting, can you type up a response to Amy's question about the uncertainty quantification?
Physical modeling, data fit. Yeah. Okay, so Mary Beth will answer the question in chat. Thank you so much. But I did have a question for Paris as well. It's very, very naive. You said hot, dry rock. First of all, how do you know that it's dry? And is that the prevalent? Is that one of the main preferred setups to have dry rock instead of having brine?
Okay. Mary Beth, can you type a little bit about what we know about the reservoir and what we've been told from Alula? So it's my understanding that what they did initially was they hired an Icelandic to do like a preliminary study on what they think their kind of system is going to be without actually collecting any kind of geophysical data. And based off that, they recommended to Alula that your reservoir is most likely going to be hot, dry rock. But in reality, I don't think we actually know if it's or not. Without a doubt, what you really want to have in geothermal is going to be like a hydrothermal type of system, like what you have in like in Yellowstone or the geysers, to where you actually have hot fluid in the reservoir. The reason why people have started focusing a lot on enhanced geothermal systems and hot, dry rock is because there's just a lot more of it. If you might have let's say just use 1 gigawatt of hydrothermal systems, you have like 1,000 gigawatt of enhanced geothermal systems. So if you really want to scale geothermal, you're going to have to figure out how to best stimulate these really hot rocks that don't have natural permeability or natural fluid, and try to optimize the fluid production out of these locations. And it's a lot more difficult than what it sounds like. Some of the issues that we discuss a lot in this group, that short circuiting problem. You can fracture that reservoir very well, but if you have one fracture just dominating, the flow from one well to the other one, you're not really going to be able to produce the amount of power that you need, or your reservoir's going to cool way too fast for it to be economical over time. So that still remains one of the main challenges with these enhanced geothermal systems, but it's not the most ideal type of reservoir, but it's just simply the one that's, the most prominent type of reservoirs you're going to be able to get.
I think we have to be careful with terminology. There's hydrothermal, which is Lauradello is a classic example, geysers is a classic example. And then hot dry rock, which is the original Fenton Hill, where literally there was no water. And then EGS is something different. EGS is stimulating natural fracture systems. Hot dry rock is artificially creating fractures. So that's the definition. So that quite clearly there may be mixing things, but in essence, EGS is stimulating an existing fracture system by increasing the conductivity of fractures and basically creating a higher conductivity. Hot dry rock is creating new fractures. And then, as I said, then that's completely different from hydrothermal, which is a completely different area. So we have to be careful that we not mix these things and make a mess out of it.
Okay, thanks, Professor.
Hi guys, Paris, I just wondered if I could ask about your fracturing with electricity, how that, what are the principles there? And like, how do you run the fracture and get the electricity to the end of
Yeah, I can,
the fracture?
I think I can pull something up to discuss that a little bit more. Okay, so this is a very simple schematic, a bare bones schematic of what this, you have an injection well and production well, let's say you have a doublet geothermal system, and that's going to be for every geothermal system, you're going to have two wells that are going to be separated by a certain distance. What we're proposing to do, in essence, is to take each well and turn it into, turn each well into an electrode, essentially. So you have one anode on one well, you have a cathode on another one, and then you flow electricity through the well. And you can flow electricity through the well because the reservoir is going to have a lot of brine. That's going to make it pretty conductive. On the surface, you'll have it's pretty simple setup. You'll have a power supply and a generator that can actually bring energy to the power supply. And the main challenge with this electric stimulation technology is that, for the most part, in a simplest scenario, most of your current density is going to be closest to the actual electrode source. So we've run a couple of models in different scenarios to where if you have a homogeneous reservoir, if you're using a DC power supply, you're only going to be able to get a lot of heating if the well was a space like 200 meters apart, like 20 meters on each side. So it doesn't penetrate all the way through. So one of the things that we need to figure out here over the next few years is what can we do to help electrically frac all the way through from point A to point B. And there are a couple of different ways I think that one can go about thinking through this process. So a couple of things that we're playing around with is the idea of putting in another artificially electric conductive fluid to help increase the overall conductivity of the reservoir. And then instead of using like a DC power supply, using pulse power supply, which works by storing a lot of electricity in a capacitor bank. And then you make really large potential differences on both edge of your electrodes, you know, up to a couple 100,000 volt. And then you actually have like a dielectric breakdown that goes all the way through the reservoir. And it's something that's been kind of discussed a little bit by Shell and Chevron, but there's a lot of different potential there. So I guess I can show this, which is a set of experiments that was done using the same electric fracturing. And this is all pretty new stuff. Like this, Shell did these experiments like 4 years ago. Well, essentially what they did was the exact same thing, but just in a lab scenario. They took a core sample and they just simply put on each end of it these electrodes. They stored it in the capacitor bank and they electrocuted the rock. And for Shell, they were seeing up to an 8 order of magnitude increase in permeability. It's still a very early stage technique. There's a lot more thought that needs to go into it, but this is the main thing that I've been focusing on for my thesis and trying to figure out, you know, what needs to happen to make this technology, you know, actually happen in the real world. It's super interesting for geothermal, particularly when compared to oil and gas. Because geothermal, you always have this double, you know, this rotor well kind of setup, and you need to be able to create fractures directly from point A to point B in order to help increase overall fluid flow. So we're looking at doing some shallow well testing with this technology here in the next 24 months.
Yeah, I was just wondering how you know, I can imagine if you've got rock, like you're saying here with a cylinder, that it's got to flow through that cylinder. Whereas in the Earth is a pretty good grounder and can absorb electricity pretty well. So I can imagine it might be tough to do it at scale.
Maybe people have done it at scale before.
Okay.
So yeah, we know it's possible.
Yeah. Okay.
I mean, yeah. So they by scale, I mean, back in like 1960, these guys in Colorado, they did it at will space up to I think like 100, 200, 150 feet. So yeah, even though it's easier to do with a cylinder, the electricity is still going to find a path from point A to point B that's going to have the lowest resistance, and it doesn't. I think it's overall pretty concentrated. Yeah. So it has been done in the field before, in shallow oil shale reservoirs at pretty low. So it'll work in the field. It's just a matter of like, how do we perfect the technique? There's a lot more that needs to go on to it.
And what breaks the rock? Is it the heat, or like what's the mechanism?
We're still trying to figure out the mechanism. There are a few different possibilities. The main thing we're thinking right now is that you're going to have the rock under natural pressure causing an initial pore pressure in the rock itself. And then you're going to have a very high thermal expansion contrast between the pore fluid and the actual mineral grains. So essentially, we think the main fracturing mechanism is going to be due to rapid thermal expansion of the actual pore fluid, causing the rock to break. And that's what Shell said as well, and what they thought was causing these observations that we're having. It's going to be breakdown or rapid pore fluid, and then breaking the rock from there.
Yeah. Interesting. No, sounds interesting.
Can you actually say something about the playoff, I should say, between or among wanting to increase the electrical conductivity, where you're then the resistance is down, so that you're going to generate less heat, and also the problem of hydrolysis or electrolysis of the water to produce gas, hydrogen and oxygen, and sort of like you're limited in the power that you can put in, or the voltage, I guess, that you can put in. How do those things all play off against one another?
Yeah, let me me try to answer this question in a different way. Give me a couple seconds. It's a good one. Okay. So this is the paper I was talking about when I said that they did this at scale before. So this is done a long time. This is the only paper they ever have when they published field results. This is done back in 1964. This is when they broke a big slunk of rock. That's simple. You go down here. Okay, so yeah, they did it up to like 90 feet wellbore spacing and shell. So these little dots just show like where they space their different wellbores and where they put the electrode. So you do, and they did this at pretty low power, like 250 kilowatts. So it's definitely possible, and we can get much more power these days. It's been 50 years. What's that can kind of answer this question is this one, figure 9. So what tends to happen naturally as you start flowing electricity from point A to point B is that even naturally the resistance of the rock is going to decrease. So you can see here the resistance started out at 120 ohms and it went all the way down to 40 ohms over the course of about a day. And whether that's due to electrolysis or whether that's due to just natural ionization of the rock itself as you start passing electricity through, the reservoir is going to immediately start to change. Both, not just from actually putting in fluid to make it more quick, but actually also from just just the response of I believe it's ionization happening as you start passing electricity through. So what that's going to do is it's going to, as your resistance goes down, it's going to increase the amount of power that you can put into the rock. And so that becomes more of like a power engineering question. Like how do you design the most optimal kind of a system that would allow you to maintain a maximum amount of power and start to change the reservoir properties. But that's one of the really cool things about this technology and its method is that the reservoir is going to respond and power is going to change that you can put in, and everything's changing all the time, and resistance levels are going down. When you think about pumping in a different kind of fluid to lower resistance to make it more conductive, I think the main thing it'll do, and this is like a DC power thing right here. But when Shell and Chevron were writing patents on this, the main thing that having that lower resistance does is that it allows you to create like an arc from point A to point B, or like or have like dielectric breakdown of the actual path between the wells, so you get that spark go all the way through, and that'll allow you to have deeper penetration of the overall electric energy into the reservoir, and hopefully break the rock a little bit better. Now, regarding the actual playback between, how much more efficient is lowering your impedance going to be on rock, I don't quite know that.
Did you just answer the question? You're not sure of the comparison between this type of technique and water hydrofracking, or was that a much more targeted answer you just gave?
Oh, sorry. Yeah, I think the question, the short answer to the question, and the question was, like if you put in a conductive fluid, how does that change your ability to fracture rock with power requirements? And what it would do initially, it would increase it'll increase the amount of power that you can put into the rock itself. And related to like how that will help you break the rock, these are still open questions overall.
Right. And the broader question of this technique compared to hydrofracking, what's your take on that?
Oh yeah, I think this technique, by in and of itself, won't be as good as hydraulic fracking. Mainly because hydraulic fracking allows you to have, I think you could break a lot more volume of rock. I think the application for this technique is to do it in combination with hydraulic fracking. One thing that we've been thinking of is if you hydraulic frac, and then you hydraulic frac like maybe like an electric conductive proppant, and now you have a really electric conductive channel. You could then follow it up and use it as a post fracking technique to widen those initial hydraulic fractures and increase overall flow. Or you could do it on the flip side to where the first thing you do is use this technique to create zones of weakness in your reservoir. And then you follow that with the hydraulic fracture, which will lower the overall pressure you need to be able to break the rock. So I look at it as more like a supplement as opposed to being a replacement in the real world. But I think it does have a place alongside hydraulic fracking to increase overall, stimulate reservoir volume.
Do you have physical reasons to believe that it would address the cold channel issue you were mentioning earlier? Like
yeah, I wrote a proposal recently on this that I can kind of I won't show the proposal, but what I was thinking regarding how this can help the short circuiting problem is what we can do with the electrodes is position them directly into the low producing fractures. And then instead of trying to hydraulic fracture those low producing fractures, we can then use this electric stimulation to make those more suitable. So that way you're widening the existing fracture path and the ones you want to connect with. And that will allow you to have more uniform flow. So that's why I think it'll fit in to the short circuiting problem.
Okay, thank you. Are there other questions from all of you?
No, just one comment, Paris, that obviously Aramco have got lots of expertise in modeling. So since it's Saudi Arabia, you might want to talk to Aramco.
Yeah, they're I think they're going to give us a lot of data.
Yeah, yeah. I mean, and they got tremendous modeling facilities, so
yeah,
it'd be an easy lift for them.
Okay. Is there an MIT experience testing the scope rocks to spend some money with these previous signatures?
So,
I'm not aware of any, Doug. Sorry, I'm just reading my I'm reading some of the comments.
It seems like lab work may be a good place to start on some of this. Electrical properties of rocks vary quite a bit with clay content and fluid content, and getting some lab work to form a basis for going forward would perhaps be a direction that could be taken.
Yeah, we've done a few different experiments on water-rich shells like Opalanis, which has a lot of like montmorillonite in it, and it appeared to work very well in these kind of clays that have a lot of inbound water into it because they're pretty electric conductive. You can actually we were able to actually create like initial fractures in these kind of rocks without having to saturate the rock at all. Which you couldn't do in a completely dry rock because it's way too insulating. Yeah, so we definitely want to test on different kind of rock samples that have different amounts of clays, especially ones that have a lot of clay-bound water in them. It's definitely interesting to do.
Mary Beth is asking in chat to John if his question was answered.
Yeah, I mean, I'm not sure. I mean, I just did a quick lookup of papers, and they're using it for drilling, electrical techniques, pulsed electric. The Russians have got some papers. So I can see that, yeah, it's possible to break rock with electricity for sure. I think it would just be control, this idea with the anodes, cathode and anode. I'm not sure exactly how that'll work.
Yeah.
Like you say, I'd go to the lab first, scale for sure.
Yeah. We've broken rocks in the lab with this before, and right now, what I'm working on is I'm working with Professor Einstein, Professor Jim, putting like a high pressure triaxial type of experiment where we're going to do this electric fracking, and we'll see how under higher pressures. It's without a doubt possible to break rocks with electricity, and the configuration that we set up, anode and cathode. It just becomes, how do you optimize it? How does the different kind of electrode spacings change the ability to do it? Is pulse more better than current, and all kinds of different questions around that. But it's a pretty open overall research field that hasn't been a lot of literature on. There has been a lot. If you look in literature on like electricity fracking, you're going to find a lot of stuff on similar to what you found previously when they use it for drilling, or when they have like electrodes close to one another, and then you pulse from that source. But the actual point A to point B type of electric fracking hasn't really been looked at too much.
Yeah, I mean, and your point as well about you need to get proppant in there to hold it open. That breaking it is one thing, but you've got to hold it open. So you're going to have to move something into the fractures, unless there's
that's definitely true. This is why no, I think you're right. Yeah.
I mean, certainly.
Yeah, I think it's going to need to work alongside.
Yeah, I think so.
Yeah, I think it's going to have to be something that you use alongside hydraulic fracking. Mainly, even the proppant question. But one thing we thought about, and that Exxon did a while ago, is they were using like electric conductive proppant. So now you always have, a really high conductivity with fracks. That's a lot easier to get current into them.
Yep, that makes sense.
Okay, Paris said it was done in the field many years ago, 1964. What data are available from that or other field experiments? Amy, I can send you the paper, but they didn't really, the only data they really collected when they did this before was total power consumed versus how the resistance between the 2 points changes with time. They also did a little bit of like flow testing to see how permeability was increased, but they didn't really provide metrics on what that looked like. And that's the only field study that I've been able to see, that I've seen in the past few years of working on this. Yeah, there was another question about how electric simulation just get better with dry rock. It'll need to work alongside hydraulic fracking when you put some kind of proppant in there, or you use it then conductivity created to then follow up with the electric stimulation to be able to help break the rock. Or if there are more geothermal resources like sedimentary types of rocks that aren't necessarily dry that we've been looking at to use with the technology as well.
Okay, any other questions, comments?
Well, it strikes me as a possible opportunity, but something probably not very studied. If you're working with highly non-conductive rocks, then you have the opportunity to consider the electrolytic hydraulic fluids and electrical and chemical properties of proppants. You might find that electricity would allow you to control a process, that you could perhaps do phase changes where you boil and condense the electrolyte, and that would be fairly dramatic in terms of forces on the rock itself. And doing that in a resistive environment might be quite interesting and tricky, and therefore a good MIT kind of topic to study.
Yeah. I'm graduating in about a year, and I'm more focused on high pressure stuff. Like how does one thing a lot of pressure would do, and we've kind of been thinking about this as well, is it's going to change that phase change or boiling point of, and so under really high pressures, that phase change is going to happen under supercritical conditions, which has super unknown consequences on the ability to break the rock. So there's a lot of really cool things when you start thinking about how phase change is going to apply from the heating process, and how that relates to pressure and how that relates to ability to break rock that maybe we won't be able to touch on right away, and I'll probably be graduated by then, but it could be something that I'll still be in Boston and we can still start touching on in the future. One of the cool things about having the startup is that it opens up a lot of doors for us when it comes to like funding for projects. We can apply to government, grants and things like that are more focused on how do you take the technology to commercialization and other opportunities there as well. So there are things that we can work on in the future, definitely, to better understand the physics of how this works in different kind of parameters that makes it work better.
Okay, thank you so much, Paris. That was very very interesting and new topics for us. We might return to those. That was excellent. So thank you so much.
Yeah, and in the future I can put together like a more specific electric fracking type of presentation. I thought we were going to be doing more geothermal stuff, but it kind of had to go on the fly, Sorry.
Right. You never know where this group goes. Yes, but this is exciting, and it brings up new questions on how to frack differently for sure. So thank you so much. I think we've reached our hour. We've reached noon time. So bon appetit, everybody, and we'll see you next week. Bye, everyone.
Thank you. Bye.